Hi, in this lecture I will introduce you about the current trends in surface modifications of the nanomaterials. This is the part 2. In our last lecture we have elaborately discussed about the doping, but in this particular lecture we are trying to discuss about some other methods. So, here if you remember, in our last lecture we have discussed about the doping, but in this particular lecture we are trying to discuss about the functionalizations. So, functionalizations is nothing but the how we are trying to modify our nanomaterials or maybe the nanoparticles, and next lecture we are going to discuss some other methods. So, first before going to start, first we have to know that what is called the functionalizations. So, here the possibility of attaching some functional groups. So, simple, in the doping, if you remember that we are putting or maybe that we are inserting some materials inside our nanoparticles, but in this particular case for the functionalizations we are not going to insert any materials into our base or maybe that parent materials, just we are attaching some kind of functional groups on surface of that nanomaterials or maybe that surface of the nanoparticles, so that we can modify these nanoparticles. So, the possibility of attaching the functional groups to the nanomaterials such as fullerene, carbon nanodots, carbon nanotubes, graphene surface with molecular moieties possessing suitable properties that are essential for the realization of new molecular hybrid materials with noble or maybe the enhanced functions. So, what I am telling that just attaching some kind of functional groups on the sideways of our nanoparticles or maybe the nanofillers, we can enhance some properties. So, here we are trying to show you some examples. So, here this one is the carbon nanotubes. So, we are trying to attach some kind of functionalized group on the surface of these carbon nanotubes, either maybe it can wrapped or maybe it can simply stick onto the carbon nanotubes, it can wrap the carbon nanotubes, sometimes it can go inside the carbon nanotubes. So, like this way we can modify the surface of that particular nanoparticles, so that it can show us some better properties. So, substitutions of carbon based nanomaterials with functional groups in the scaffold and or in the periphery is a viable approach to improve their stability, dispersibility, thus processability, and provide tools to introduce new functions that can be used to further tune their properties. So, by attaching these functional groups, either we can enhance some existing properties or maybe sometimes we can add some extra properties to that particular material. Functionalizations with photochromic molecules including azobenzenes, diarylethanes and the stilbenes can be achieved either through non-covalent or maybe the covalent approaches. So, when we will come into the details of the functionalizations or maybe how we are going to the functionalizations, we will see that what are the methods. So, actually the two methods, one is called the non-covalent and another one is the covalent. By these two methods generally we can do the functionalizations of any nanoparticles, and this literature has been taken from the Nature Communications, and it has been done or maybe it has been given by the scientist named Zhang. So, he has actually presented this paper, these results in his research paper. So, here we are trying to show you that there are several types of functionalizations and how we can classify those. So, first is called the functionalizations, which is divided into two types. One is called the chemical functionalizations, another one is called the physical functionalizations. The chemical functionalizations is divided into two, one is called the sidewall, another one is called the defect, and the physical functionalizations is divided into three parts. One is called the polymer wrapping, then surfactant absorptions and the endohedral methods. So, here it is divided into two classical zones, one is called the chemical functionalizations and the physical functionalizations. So, first it is coming to the chemical functionalizations. So, chemical functionalizations is based on the covalent linkage of functional entities onto the carbon scaffold of carbon based nanomaterials like carbon nanotubes, graphene, reduced graphene oxide, etc. So, here the thing is that the chemical functionalizations when we are going to do, we should have the covalent linkage in between the functional entities and in between the parent material. Then direct covalent sidewall functionalizations is associated with a change of hybridization from sp2 to sp3 and a simultaneous loss of pi conjugation system on graphene layer. So, simple by the covalent linkage these materials or maybe that these functionalized materials will attach onto the sidewall of the nanoparticles itself. The fluorinated carbon based nanomaterials have carbon and fluorine bonds which are weaker than those in alkyl fluorides. Successful replacements of the fluorine atoms by amino, alkyl and hydroxyl groups have been achieved. Cycloaddition is another method which includes Diels-Alder reaction, carbene and nitrine additions, chlorination, bromination, hydrogenation and azomethane halides. So, these all are the materials by which we can do, or maybe these are the different techniques by which we can do the modifications or maybe the functionalizations of our nanoparticles. Then defect functionalizations. So, here from this name itself we can do that when we are using certain kind of nanoparticles or nanofillers, some defect sites are present at the sidewalls of these nanomaterials. So, when we are doing this kind of functionalization, simple these functionalization materials is going or maybe is attaching with the defect sites of this kind of nanofillers. So, defect sites can be at the open ends and or holes in the sidewalls, pentagon or heptagon irregularities in the hexagon graphene framework. Oxygenated sites can also to be considered as defects. So, here generally when we are talking about this kind of carbon nanotube structure, we can find that there is some kind of defect sites. So, on that particular defect sites the functional groups is attaching directly. So, defects can be created on the sidewalls as well as the open ends of the carbon based nanomaterials by an oxidative process with strong acids such as sulfuric acid or maybe that nitric acid or a mixture of them, or with strong oxidants such as potassium permanganate, ozone or maybe the reactive plasma. So, here sometimes what we are trying to do, if we are trying to modify some kind of nanoparticles or maybe the nanofillers, maybe sometimes we are creating the defects on its surface. So, by applying this kind of strong acids or maybe some kind of other base materials or maybe the strong reagents, so that the defects can be created on the sidewalls or maybe the at the face or maybe the at the end of that particular nanomaterials, so that simple the functional groups can come and attach at that particular defect sites. The defects on CBNs created by oxidants are stabilized by bonding with carboxyl acid group, that is COOH or maybe the hydroxyl OH groups. Due to this, functionalized CBNs become soluble in many organic solvents, because we are putting some kind of carboxylic group or maybe some kind of hydroxyl group on this particular nanofiller, so that it can soluble into some solvent. Chemically functionalized CBNs are able to produce strong interfacial bonds with many polymers, allowing CBN based nanocomposites to possess high mechanical and the functional properties. So, by just adding the different functional groups on to the surface of that particular defects of that particular nanofillers, we can modify this kind of nanofillers and it can be give some kind of functional and some kind of mechanical properties. So, here is an example that how we are going to do by direct sidewall functionalizations and the defect functionalizations. So, when we are talking about the direct sidewall functionalizations, from this particular figure you can understand that whatever the modifications we are trying to do, we are doing onto the sidewall of that particular nanofiller. So, here suppose we are doing the amine substitution over there, or maybe some fluorine substitution over there, or maybe some kind of alkyl or maybe aryl group substitution onto the systems. So, fluorinations and derivatives reactions reaction is going on. So by which this amine group or maybe that fluorine group can attach at the side walls of that particular nanofillers. And also we can do by this method by some kind of hydrogenation, so that hydrogen bonding or maybe H can be attached to that particular systems. We are doing some kind of cycloadditions, so some kind of nitrine groups, maybe carbene groups, then diels alder, maybe some kind of nucleophilic cyclopropanations. So these kind of materials can be easily attached at the side wall of that particular nanocomposites or maybe the nanofillers. Not only that, some kind of radical also we can attach to that particular systems. So these all are coming onto the direct side wall functionalizations. So when, and it is mainly we are doing onto the single wall carbon nanotubes or maybe the multi wall carbon nanotubes. But when we are doing the defects functionalizations, so as I told already in my last slides, the defects means either the defect is already presented inside that nanofiller, or maybe sometimes we are creating the defects onto that nanofillers to modify or maybe the functionalize the nanofillers. So in this particular case we are doing some kind of amidations onto the defect sites, we are attaching some kind of ester groups onto the defect sites, maybe thiolations or maybe some kind of silanations we are doing onto the defect site itself. Not only that, sometimes a polymer grafting also we are doing, but this particular topic we will discuss in our next lecture. So here by this way, one is the side wall, another one is the defect, we can do the functionalizations of this kind of nanofillers. Then here we have tried to show some kind of chemical functionalizations of the graphene, how we can do the chemical functionalization of this graphene. So we can do the H functionalizations. So from this particular figure you can see that graphene is like a sheet, so it is a 2D material. So here we can attach some kind of functional groups at the edges of the graphene, so that we can do the modifications, we can do some basal plane functionalizations which the functional group attach at the basal plane of that graphene sheet. Sometimes we are attaching some kind of non-covalent adsorptions on the basal plane, sometimes we can do some asymmetrical functionalizations of the basal plane. So one side the groups will be different, the another side other groups will be attached. Sometimes we can do by layer functional modifications also, so it is called the self assembly of functionalized graphene sheets. So by these methods we can do the chemical modifications or maybe the chemical functionalizations of graphene. Next we are going to discuss about the physical functionalization process. So from the name itself you can understand that we are doing this functional process by some physical methods. So functionalization of carbon based materials or maybe carbon based nanoparticles using covalent method can provide useful functional groups onto the CBN surface. Non-covalent functionalization is a method for tuning the interfacial properties of nanotubes. The suspension of CNTs in the presence of polymers such as polystyrene lead to the wrapping of polymer around the CNTs to form the supermolecular complexes of CNTs. So here you can see that we are using certain kind of carbon nanotubes, either maybe it is single wall carbon nanotubes or maybe the multi wall carbon nanotubes, and the side walls is wrapped by some kind of polymer or maybe the polymer chain. So by wrapping the polymer onto the carbon nanotubes we can do the functionalizations or maybe the modifications of the carbon nanotubes material. And also the physical absorptions of surfactant, that is also another technique. On the CNT surface, lower surface tension of the nanotubes effectively preventing the formation of aggregates. Surfactant treated CNTs overcome van der Waals attractions by electrostatic or maybe the steric repulsive forces. The efficiency of this method is strongly dependent on the properties of surfactants, medium chemistry and the polymer matrix. So here whatever the materials we are trying to use, sometimes we are trying to increase its absorption property so that it can absorb certain kind of other functionalized materials towards it. So by this way we can do the modification or with the functionalization of that particular nanofillers. Then there is also another methods or maybe another classical approaches by which we can do the functionalization of our nanoparticles, that is called the endohedral method. So in this method, guest atoms or molecules are stored in the inner cavity of the CNTs through the capillary effect. So you know that what is the CNT? The CNT is nothing but it is a hollow tube. So its both the end are open and it is like a pipe. So if there is having a one layer of that particular material, so we are calling it as a single wall nanotube. When there is having the multiple layer, we are calling it as a multi-wall carbon nanotubes. When we are having only two layer, we are calling it as a double layer carbon nanotubes. So it is a very good promising materials from the carbon family. So the insert is totally the hollow one. So what we are trying to do? We are trying to incorporate certain materials inside this hollow tube, so that by doing this one we can do the modifications, because till now we are talking that we are adding some materials on the top of the surface itself. Not only that, we are trying to attach some functional group on the defect sides of the materials, but in this particular case what we are telling that we are inserting some materials inside the holes or maybe inside the pipes. What are those materials? The insertion often takes place at defect sites localized at the ends or on the side walls. The insertion of inorganic nanoparticles into the tubes such as C60, which is nothing but known as the fullerene, then some kind of silver particle, then gold particle, and the platinum is a typical example of endohedral functionalizations. So simple, we are inserting certain kind of fullerene materials, some kind of silver particles or maybe the gold particles or maybe the platinum particles inside the carbon nanotubes. Small biomolecules such as proteins, DNA, because that is a very promising area for the biomedical applications. So when we are trying to do or maybe we are trying to make certain kind of proteins or maybe some kind of enzymes or maybe some kind of DNAs or maybe the RNA, simply we are inserting into the nanofillers and whole thing we are putting inside our body. So can also be entrapped in the inner hollow channel of nanotubes by simple adsorption process, forming natural nanotest tubes. So it can be done in our laboratory. It is the simple methods. By doing also we can do the modification of this kind of nanofillers. The combination of these two materials, that is carbon nanotubes and the guest molecules, means what we are inserting into it, either maybe fullerene or maybe silver particle, gold particle, platinum particle, or maybe some kind of bioactive materials like proteins or maybe some kind of serums or maybe some kind of RNA or maybe the DNA, is particularly useful to integrate the properties of the two components in hybrid materials for the use in catalysis. Maybe we can use that materials for the catalytic applications, some energy storage applications, maybe some supercapacitor or maybe some energy storage devices applications, then nanotechnology and the molecular scale devices or maybe some biomedical equipments. Next, we are trying to show you that what are the advantages and disadvantages of various carbon nanotubes functionalization methods. So when we are talking about the chemical methods, it is divided into two. One is called the sidewall and another one is called the defect. So when we are talking about the sidewall, the principle is that hybridization of carbon atoms from sp2 to sp3. Possible damage to CNTs? Yes, of course it is possible. Easy to use? No, it is not easy to use. Interactions with polymer matrix is S, means that means it is very strong, and re-agglomeration of CNT matrix always it is possible because we are using very tiny particles of that nanofiller. So when you are trying to mix those filler inside our polymer, due to its large surface area and high aspect ratio, always they are try to agglomerate. So that is the main drawback of using this kind of nanoparticles into some matrix or maybe some into some alloys or maybe into some blends. Then when we are talking about the defect, generally the principle is the defect transformations. Possible damage to the CNTs? Yes, of course possible. Easy to use? It is very easy to use. Interaction with the polymers is very strong. Re-agglomeration of CNTs in matrix is possible. Then when we are talking about the physical method, when we are talking about the polymer wrapping onto that particular nanoparticles, the principle is due to the van der Waals force or maybe the pi stacking. then possible damage of the CNT is not possible, because just we are wrapping one material on top of that. Then easy to use, of course it is possible. V means variable according to the miscibility between matrix and polymer on the CNT, because that is the adhesion in between the polymer and the carbon nanotubes. And then re-agglomeration of CNTs in matrix, that is also not possible. Then when we are talking about the surfactant absorptions, generally this is based on the physical absorption process. Possible damage to the CNTs is not possible. Easy to use, it is easy, it is very weak interactions with the polymer matrix, then re-agglomeration is not possible. When you are talking about the endohedral method, it is generally based on the capillary effect, because whatever the material we are trying to insert, due to the capillary effect it is going inside that tube or maybe that inside that material. So possible damage of the CNT is not possible. Then easy to use, it is not also easy to use. Interaction with the polymer matrix is very weak, because whatever the functionalized group we are putting, that is going inside the nanotube, not the surface. And re-agglomeration of CNTs is matrix is very good. So here what are the approaches that by which we can do this kind of functionalizations? So first one is called the non-covalent functionalizations, and second one is called the covalent functionalizations. Then here for the non-covalent functionalizations of carbon based nanomaterials is typically based on the physical absorption of functional units of carbon materials, like the pi interactions or maybe the pi bonding in between the functionalized groups and your nanofillers or maybe the nanoparticles, or sometimes it is called the pi stacking, hydrophobic interactions or maybe some kind of electrostatic interactions. But when we are talking about the covalent functionalizations between carbon based nanomaterials and functional units via condensation reactions like amidations or maybe the ester formations or maybe the esterifications and the acid treatments. So here by two methods, one is called the covalent method, another one is called the non-covalent method, we can do the functionalizations of these kind of nanoparticles. So here these all are the materials which we are going to do the functionalizations. One is called the carbon nanodot, then it is a 0D fullerene, 1D carbon nanotubes, 2D graphene sheet and polycyclic aromatic hydrocarbons. Then by cycloadditions we can do the modifications, it is known as the covalent modifications, and then condensation reactions also we can attach some kind of groups, mainly amine groups onto the surface. Then we can do some kind of polymerizations onto the graphene sheets or maybe that graphene flakes, and not only that, below one is called the non-covalent modifications, where we are doing some kind of pi stacking or maybe the pi interactions in between the functionalized groups and in between the your carbon nanotubes. Then we are doing some kind of hydrophobic interactions over there, and also we can do some kind of electrostatic interactions onto the graphene surface. So some kind, due to some kind of hydrogen bonding or maybe some kind of electrostatic bonding, we can do this kind of non-covalent modifications, and here this is known as the photochromic molecules which is attaching to the surface. So here the whole picture is about the functionalization of carbon based nanomaterials with the functional groups, by which just simply we are trying to show that how we are doing the covalent functionalizations and how we are doing the non-covalent functionalizations. So now in this particular slide we are going to show you that how the interaction is going between the functional groups with the host materials. So as I told already, so generally there are two things, one is called the covalent bonding, another one is called the non-covalent bonding. So two types of pi interactions occur between the electron rich and electron poor regions, which influence its interactions with other molecules or nanomaterials. So as I told in my last slides, that this is the main vital factor by which the functionalized group attaching to the nanomaterials, that is called the pi interactions or maybe the pi stacking or maybe the pi bonding. So for graphene oxide or more so for reduced graphene oxide, the basal plane is relatively similar to graphene except for defects by epoxides or hydroxides bound to the carbon atoms. So here in this particular case you can see that when this functionalization is taking place, simple the pi bonding is taking place, but in this particular case when you are doing the modifications, it is having the carbon atom, then it is having the hydrogen atom, then first carbon is attaching with the hydrogen, then through hydrogen it is having having the pi interactions in between the nanofillers and the functionalized group. Here also the hydrogen bonds and other pi stacking with the graphene oxide sheets is taking place. In some places the hydrogen bonding is taking place, some cases the pi bonding is taking place. Here this is also the another good examples that idealized pi or maybe that carbon hydrogen pi interactions from benzene, naphthalene or maybe the pyrene molecules above and below the basal planes of the graphene. So as I told already, some groups are attached on top of the sheets, some groups are attached the bottom of the sheets itself. So sometimes it is going to get the pi interactions, sometimes it is going to get the carbon hydrogen pi interactions. So this is also some kind of literature review studies, and this has been done by the Georg Gakilas and he has been presented this paper in some chemical review journal in the year of 2016. So here are the some examples of the functionalized groups with enhanced properties. What are those? First is that we are using the host material as a graphene. Then what type of functional group we are trying to attach? That is benzoyl peroxide, and attachment is covalent type, means covalent bonding is taking place. Then property enhancement, generally electronic and optical properties is going to be enhanced, and it has been done in the year 2016. When we are talking about the carbon hydrogen some kind of host materials, we are attaching that alicyclic amines. It is also be doing by the covalent bonding. It is having some pharmacokinetic property enhancement is taking place. It has been also done in the year 2016. When we are talking about the graphene, we are using some kind of dibromocarbene and attachment is covalent, generally optical and electronic properties is enhancing. It has been done in the year 2016. We have done some modification of reduced graphene oxide by the ruthenium oxide group, because ruthenium oxide is the functional groups which is attaching to the reduced graphene oxide by the covalent bonding, which is nothing but the enhancing the electrochemical properties of that particular material. It has been done in the year of 2015. Then we have done the modification of transition metal dichalogenides, graphene, maybe some wood based cellulose fibers, or maybe some carbon nanotubes. Carbon nanotubes we have done the modification by carboxyl group and hydroxyl group. It is also one kind of covalent bonding. So for the electrical and mechanical properties enhancement, we have done this kind of modifications. So it has been done in the year 2014. So here also we have done also some modifications like carbon nanotubes with the porphyrin derivatives. Maybe it can be attached by the covalent functionalizations or maybe the non-covalent functionalizations. It can increase the optical and electrical properties of that particular material. It is little bit older. It has been done in the year of 2013. Then we have done some kind of modification of the silicon carbide surface. We have done the functional groups, whatever we have used is that organosilanes. So it is also a mixture of some amino propyl diethoxy methylsilane and the octodecyl trimethoxysilane. It is a mixture, and then attachment is covalent types. Then property enhancement is generally electrical and chemical properties. It has been enhanced in the year 2013. We have done the modification of fullerene by the imidazo lines. It is also a covalent types. It is having some unique synthesis process. In the year 2013 it has been done. Again we have done the modification of graphene by aryl diazonium, covalent bonding, solubility, electron mobility and sensor activity. So that is also some added advantage that we are using these materials for the sensor applications. And not only that, it has been done in the year of 2011. Then we have used some modifications of the graphene nano ribbon, where we have used the 4 nitrophenyl groups. It is also the covalent types bonding has been taken place. It has been enhanced the electrical properties of that particular material, and it has been done in the year of 2010. So here we are trying to show you some examples that how we are functionalizing the graphene sheet from the graphite. So here first what we are doing the oxidations of the natural flakes of graphite to graphite oxide, followed by the ultrasonications. Here I am having the graphite sheet. Graphite is the simple method, whatever we are using in our pencils or maybe some other materials. It is very easily available from the environment itself. So we have to collect those graphites, then we have to do the oxidation process of that graphites, and the vigorous sonications can be taken place, by which some acid group or maybe some hydroxyl group will be attached on that graphite sheet and it will become the graphene oxides. Then after graphene oxide we are doing the amine modifications over there. So some amide group is attached to that particular graphene oxide. So actually the graphene oxide is having that there are so many functional groups are attached with the graphite sheet. So when after that we have to do the reduction process, that reduction also can be done by different methods. One is called the NaBH4 modifications, or maybe sometimes we can do it by the hydrothermal treatment. So by the hydrothermal treatment also we can reduce that graphene oxide to the reduced graphene oxides. So here by these methods simply we can delete some functional groups so that the single layer graphene or maybe some few layer graphene can be observed for particular things. So aqueous graphene oxide dispersants is treated with alkamine to obtain the amine modified graphene oxide. Then amine modified graphene oxide is reduced using hydrogen hydrate to produce the amine modified graphene. So like this way we can attach some functional groups to that materials, and then like this way we can reduce it to the reduced graphene oxide from the graphene oxides. And also it has been taken from the Progress in Material Science, which has been published in the year of 2012 by the Quilla et al. So here we come to the summary of our particular lecture. So we have discussed various functionalization techniques for carbon based materials. Influence of functionalization on stability, dispersibility or processability of carbon based nanomaterials has been discussed. Different approaches of functionalization have been done in this particular case. In this particular case also functionalization of nanomaterials with amines, carboxylic acids, azobenzenes etc. have been studied. Some examples have been covered in this lecture which shows different ways adopted for modification of new and advanced nanomaterials, but those examples are very few. So actually we have done last lecture we have done about the doping. In this particular lecture actually we are trying to give you a glimpse of the functionalizations. So if you remember, we just for your knowledge once again I am telling you that functionalization is taking place by the two methods. One is called the by sidewall, another one is called the defect sides. So functional groups you can attach onto the sidewall of your nanomaterials, or maybe you can create certain kind of defects onto your nanomaterials so that functional groups can directly go to the defects, or maybe some defects are already present onto your nanomaterials, you can attach that functional groups to that particular defect sites. Now again we have discussed that how the bonding is taking place. Some cases we have shown that generally the covalent bonding or maybe by the non-covalent bonding. We have shown you the pi-pi interactions or maybe the pi-pi stacking or maybe the pi-pi bonding in between your functionalized groups. We have shown you the hydrogen bonding over there, or maybe some kind of low molecular bonding also we have shown over there. Then based of these bondings how we are trying to modify our nanofillers, we have given some kind of sorts of examples over there. Then also the last one is called thank you.